we'll cover quite a broad variety of topics. But of course, what they have in common is methodological innovations in one or the other dimension that is relevant for integrated assessment modeling, including uncertainties. I think that's an evergreen of integrated assessment analysis, how to deal with those. Then harmonization across a larger group of IAMs, particularly relevant for multi-model studies. Then methods to assess solar rooftop potential, so spatial type of analysis to create data sets that feed into integrated assessment models, downscaling methods to the country level, and then the topic of impacts of air quality on health and agricultural productivity. So I'm very much looking forward to this broad range of topics. Let me also not spend any more time on this introductory part, but right away pass the floor over to Tommi EKHOLM, who I see is ready to share his analysis on, or his insights on dealing with deep and endogenous uncertainties in integrated assessment models. Very glad to see you, Tommi, and the floor is yours.
Thanks a lot, Volker. Nice to see you also. Hello, everybody. My name is Tommi EKHOLM from the Finnish Meteorological Institute. And yes, as Volker said, I'm going to talk about uncertainties, how to deal with deep and endogenous uncertainties in IAMs. So dealing with uncertainties and probabilities, the kind of standard methods that people typically use, usually there's like a couple of limitations. You kind of often assume that the probabilities that you consider in some kind of a model, let's say some stochastic IAM or something else, that the probabilities are unambiguous and exogenous. And what these mean, that the unambiguous means that you can express the uncertainties by unique probabilities, and exogenous means that the probabilities come from somewhere else, are not affected by what's happening inside your model. They are not affected by earlier actions. But there's been kind of new methodological development in both of these branches. So these are kind of two distinct things, and I'm just going over a bit of development that I've been working on this with different people. So on ambiguity, this is based on a paper that was just published this year that we did with Erin Baker from University of Massachusetts. And the endogenous uncertainties is something that we are working with Olli Herrala and Fabio Oliveira from Aalto University. And this is still kind of work that is being finalized, but there's also a link for code that is already ready if somebody is interested to try that out. There's also some code as a supplement to that management science paper if somebody wants to try out kind of the simple example that I'm going to present next. So what we mean by ambiguity is that there is like some kind of an uncertainty that we really can't express with just a single set of probability distributions. An example related to IAMs is maybe this probability distribution of climate sensitivity. This one figure is from Knutti and Hergel, maybe a bit old paper already, but I think it illustrates nicely the idea. They went through quite a bit of different kinds of evidence for climate sensitivity, but tried to combine those two, but couldn't go into like a one single distribution, but instead decided to present two distributions where they have a bit different characteristics. There's like a thicker tail for higher climate sensitivity in one, and the other is more like even. So this would be something that you could consider that there is maybe a set of beliefs instead of a single probability distribution that can be seen as plausible to describe this uncertain parameter. And what we did in this paper with Erin, it's kind of a continuation of work from others, is that we create this kind of a dominance relationship between these beliefs that you or some decision maker consider plausible. So in a way that you can calculate some measure, expected utility, for example, some expected value that you're interested, and you calculate that with all the beliefs, all the probability distributions that you consider here in this set of beliefs, set of probability distributions. And that will get you something like, if you have two beliefs, that will get you something like this, different strategies, different outcomes measured in terms of both of the beliefs. And there are some methods that are then try to combine that. What's the combined best strategy? But we instead were exploring this kind of a dominance concept, bit or very much similar to Pareto dominance, Pareto optimality, if that's a familiar concept. But here, instead of criteria, is just over different sets of beliefs. So in a way, you want to find these non-dominated strategies that seem to be good, in that sense that you can't improve the strategies in terms of both beliefs, but maybe have trade-off between the two. And you want to avoid the strategy that are dominated, because there's like other strategies that are strictly better in terms of both of these beliefs. So we did a simple IAM example of this kind of minimizing mitigation cost and climate damages while considering uncertainty in learning in both climate sensitivity and the expression of climate damages. And then we had multiple beliefs over the probabilities of both the climate sensitivity, and that was actually directly from that Knutti and Hegel paper, and then the damage exponent of Dye's type of damage function. And for that, there's no practical kind of good data source, so we just made illustrative examples. So what you get then from this kind of a simple, super simple IAM is a set of non-dominated mitigation strategies with different beliefs over the climate sensitivity and the damage function. And what you see is kind of that the blue area between all of the curves is kind of the non-dominated area that you could kind of somehow argue that it's not bad, at least, but you just make in this area, you make trade-offs between these different beliefs. So the outcome from this kind of a thing is that you don't get a single optimal emission strategy or emission pathway, but instead this kind of Pareto front between different beliefs, and it still can give you some kind of a range where you which suggests that where you roughly should be heading to. And here, like, even if we consider very different kinds of beliefs for climate sensitivity and damages, it still shows that there's kind of a quite large need for mitigating climate change and reducing emissions. But based on what kind of beliefs you have, there's more or less of mitigation in this non-dominated set. Okay, so that was a quick overview of that. You can check the paper if there's more interest into that, but I'm jumping then to this other topic and giving also a brief description of that. So what we mean by decision-dependent uncertainties is something that there is an uncertain event, but that's affected by your earlier actions, your earlier decisions in the model. So there's two things that we consider in this paper that I I mentioned. Either the earlier action affect directly the probabilities of some uncertain events, or then there's some information revelation that's dependent on what you have been doing. A simple example that you could have some kind of research and development and deployment of a certain technology, and that affects the future cost of that technology, which are uncertain. But if you do more of that, you're more likely to get lower costs, for example. For information revelation, there's maybe an example that you could do like more climate research, and then by that you would get more early or with better probability some observations from important climate parameters like climate sensitivity and climate impacts and damages in that sense.
2 minutes.
Yes. So we did a similar simple IAM example that was on the previous slide, but we included these kind of research and development decisions that you could do impact analysis for climate change impact, and then observe what the climate damages are. You could do similar research on climate sensitivity and then observe better what the climate sensitivity is, or you could do mitigation technology R&D and get a reduction in mitigation costs. And that these kind of, then there's a model that does analyze or kind of consider these decisions and what their outcomes on or with different probabilities, and then there's a similar kind of minimization of mitigation costs and expected damages. And we are still kind of trying to finalize how to present the results, so it's not super clear at the moment, but kind of the main takeaway from this is, well, there was some problems with getting reliable data, and some of the parameters we use are more or less kind of fabricated, but still kind of wanted to do this example. So what we get out of this kind of model that, well, do all the research you can, because the information you might get from that is so valuable. The technological R&D affects strongly the ambition of mitigation, so there's high probability to get lower mitigation cost, and that's really a good thing. And knowing about the damages or climate impact seems to be more important than knowing about the climate sensitivity. But yeah, those are kind of stylized outcomes what we get at this point from the model.
Time over.
Okay, yeah, just quick conclusions. There's new methods to do these. There's code available to try this out, but there's some challenges still. What's optimal for ambiguity, and then how to get reliable estimates for decision-dependent uncertainties. And that's about it. Thank you.
Thanks a lot, Tommi, for the interesting presentation. One of the takeaways from your paper is it's really a golden era of science that we're heading, because the high-level conclusion that we should do all research that we can do is, of course, something that we like to advise policymakers on.
Exactly.
With many uncertainty methods, one of the challenges is they work really nicely in stylized examples and settings, but they become really cumbersome, if not impossible, to deploy with kind of full-scale process-based IAMs that are usually deployed. So from that perspective, what we often see in those settings being deployed is methods that basically rely on large scenario ensembles, Monte Carlo style type of simulations, that because that's basically just running the model n times, where n can be very large, but that's very doable, right? So what would you say in terms of this method? I don't know to which degree, if you looked at it, how scalable is it?
Yeah, that is really a point of concern, that considering these uncertainties probabilistically does make the problems much more harder to solve, and that creates like a problem in using them for these large-scale IAMs, which are quite often quite heavy to solve in the first place. So yeah, they are more restricted by that, maybe to kind of stylized, but still kind of you can still include certain degree of kind of process descriptions, and so it's not entirely stylized, but you can have, for example, like a simplified climate model there running, and some kind of representation of some processes. But yeah, it's not possible maybe at the moment to run them in these bigger models. But yeah, then there's like a interesting kind of would there be some way of combining these probabilistic approaches then with like running distinct scenarios, because that has been like the main approach that's being done in bigger models, and kind of this set of scenarios then gives you some idea about the uncertainties.
Thanks, Tommi. Useful to know. We have one more question from Pedia in the chat. Do you want to come forward and ask yourself?
Yes, yeah. I can come forward. I'm in a municipality, so I'm outside my house, but thank you for the nice presentation. I was just wondering, you were mentioning the R&D of damages and R&D of the climate signal. I was just wondering, you mean by damages the damage functions, right? You mean the research into damages is more important. Research into damage functions is more important than the CS, right? Just
yes, exactly. Yeah. So kind of we represent like damages over the damage function, and there's like a certain parameter that we then vary or keep as an uncertain. But I was kind of referring to that the damage function, of course, like represents impacts and their valuation on climate change. So how in practice one would get some new information about the damage function would be related to knowing the impacts better, and then getting a better idea of how to value those impacts. That was maybe the idea that I was trying to convey there.
Thanks a lot, Tommi, for clarifying that. Yeah, we should actually move on to the next presentation by Sara. She's going to talk about a framework that will help us to harmonize across integrated assessment models in multi-model studies. Let me actually note that there was a related talk yesterday in one of the national sessions that presented some of the insights, and there were already then quite a few questions popping up related to the harmonization approach and how that worked along the different dimensions that you're tackling. So I think very much looking forward to your presentation, and maybe we can clarify and go a bit further into this in the discussion. Thanks a lot. Sara, the floor is yours.
Okay, so essentially this presentation is really about the methodology that we used to harmonize the studies for the multimodal intercomparison work that was presented yesterday about the projected emissions, extending the current policies. And so essentially we developed a stepwise approach for the harmonization, and that was used at the same time to reduce the variance across the models, as well as enable us to understand the behavior of the model themselves. So these work, if you're interested, we'll have the further details represented in the paper that we published over the summer on the science of the total environment, and also on the Paris Reinforced website. There's an interactive platform for displaying basically you can browse the dimensions of the harmonization that you might be interested in seeing. So The step-by-step approach that was developed for the harmonization basically was essentially an addition of layer after layer of harmonization, starting from a reference scenario. So we overall had 4 scenarios that we developed, and the starting one, the reference R, is basically the one that contains the modeler's own assumption. And it's marked with the letter R. You would see on the you would see in the chart that's the chart would represent basically the magnitude of the variance across the model. So now, as we progress with the addition of further layers of harmonization, then the gap will basically reduces. But let's progress with the description of the scenarios. So from the reference, we then add a socioeconomic harmonization and basically a database of up-to-date trends for GDP and population based on the SSP2 was developed and then was harmonized across all the studies of the models. Sorry, and that's the scenario which we called SH. Then a cost harmonization scenario was developed. CSH is the acronym because we add this cost harmonization on top of the socioeconomic one. And finally, the policy. The policy aspect, the policy dimension was also developed as a further dimension of harmonization, and the final scenario is BCSH. So now we are going to see essentially the implications of moving across these scenarios. And one thing to mention in the first instance is that we identified key differences regarding the solution approach and the technology granularity of the 6 global models included in the study. And essentially, we identified primary differences between optimization bottom-up models like the TM Grantham approach and simulation bottom-up modeling approaches as those shown and used in GCAM and MUSE. Then we also have a macroeconomic top-down model, E3ME, and 2 computable general equilibrium models, so Gemini and ISIS. So primarily, one of the differences which I need to mention, like to start with, that represented an aspect we have to deal with constantly was the technology granularity, which varies considerably across these models. So there's a high level of heterogeneity in the technology granularity, and especially between the bottom-up group and the top-down group. So, let's move to the description of the results. So the step 1 is essentially where we see the effects of the socioeconomic harmonization. And so you see scenario R, the reference, and the socioeconomic scenario SH. So the what I'm going to display is essentially the global emissions primarily, but I'm going to focus on 2030, on the 2030 differences, because the 2020 is still too close. It's quite close to the last updated year in each model. And for the models considered, it was a year in between 2015 and 2020. So it's still, it is very close to the calibrated years. But the paper would report like a further discussion of the final energy across the sector. So for the sake of time, I'm going to present primarily emissions, global emissions, emissions from energy and industrial processes. So moving from the reference to the SH, to the socioeconomic harmonization path, then we see that normally the deviation is varies across models, and primarily is dependent on how different the original assumptions of which model basically were. So Muse and Gemini, for example, would have a larger gap compared to other models. One thing that it is important to consider here is that the energy service elasticity to the socioeconomic drivers was not harmonized across the model. So that is still a level of uncertainty, a level of variation that we kept. So so this to start with, then
2 minutes.
Yeah. Yeah, okay, I'm going to be fast. So the second level is the technologies aspects, the technological harmonization. So here, just to clarify from the beginning that we only had a cost, the full cost optimization, full cost harmonization, primarily for the bottom-up models, because the top-down had different ways of technology granularity. But the sector where we had primarily consistent harmonization was the power and transport, but road transport. Just to say quickly that for top-down models, the representation of the power sector, which was indeed the one where we had a closer representation of the technologies, still had a lower granularity for top-down models as opposed to the bottom-up ones. So that is still a level of variation. For example, ICES didn't include the carbon capture technologies. And okay, so this is the results and the effect that you would see. The divergence obviously depends obviously on the primary assumptions on the reference. And then the last level of harmonization, the final one, is the inclusion of policies. So we started from the policies developed during the climate policy database of CityLink, and added policies for selected regions, US, Brazil, and Europe, for example. But we have a different coverage across regions. So you will see that the dark green areas are those most represented. In a similar way, the sectors most represented would be power and transport in terms of policies. And yeah, that's the final effect on emissions due to the policy inclusion. So that you would see that there's a remarkable, that it is a level that is quite necessary to add because of, in order to lead and guide the path of the short and mid-term for the EM's projections. So this is one. All right, good, very good. Finished.
No, you wrap up, please. It's 10 minutes now.
Okay. So essentially, it's the so what we showed is that with the step-by-step approach, we reduce the gap of the emissions to less than 2.3 gigaton in 2030, which is an important level of harmonization. And we use the harmonization to do a diagnostic on the behavior of the models. So we had still residual differences due to technology granularity, and these are barriers that we can't remove from the model and from the model use. But we understood where these differences came from, especially from the technology granularity in selected sectors like transport and industry, or an harmonized parameter like those for the building sector. And we could identify differences due to model behavior, for example, in the level of electrification in buildings due to the agent-based modeling. And that's the end of the presentation. So thanks very much for your attention. I'm sorry if I used more time than allowed.
I see there are 2 questions coming in from the chat. There is Pedia and then Bechnam. Do you want to come forward again, asking yourself?
Yeah, thanks a lot for the presentation. My question was that the figure that you showed after the harmonization of the policies, it showed quite a good convergence for the emissions, and all the models try to reach to the same level. But the one for final energy was not, as far as I understand, as good as the emissions, or the convergence was not at the same level. Is there any specific reason, or if you?
Yeah, I can expand on that. Yeah, so essentially, with the way that we implemented the policies, and as well as all the layers of harmonization, it basically the models that apply the harmonization step could implement it up to the level that was possible for the technology granularity. And so we found that specifically we had certain sector representations that was not the same granularity level across the model. So we still had this level of these differences. We had to say that the share of because I didn't show it here, but the share of the fuels is relatively closer, and but the absolute value that would vary depending also on assumption related to the the energy service projections, as well as the representation of the technology in each sector, because I need to say that we could not implement, for example, all the policies in transport. So, for example, one of the things that I can mention is that all the policies in the transport sector were applied to a good level of degree for the bottom-up models. It was not possible to apply the same for the top-down ones because they didn't have the technologies, like the same granularity. So at the same time, we noticed that the top-down model could be stronger on system-wide, cap, like in terms of emissions. So, like the emission allowance scheme. So it's a difference that would come inherently from the aspects of the model structure. And so there's a heterogeneity.
I think we need to move on to two presentations still to cover in this session. The next one is by Fabio SFERRA about downscaling IAM results to the country level, presenting a new algorithm here. Fabio?
All right, so basically today I would like to talk about a new downscaling algorithm for downscaling regional internet assessment model results to the country level. The main motivation is that internet assessment models are widely used by researchers to assess the feasibility of the Paris Agreement long-term goal, but the resolution of internet assessment models, it is often limited to a few regions. So, of course, modelers are working on enhancing the regional resolution of IAMs. Now, many of them has also a flexible configuration of regions, but it is still difficult to find the solution for all the countries in the world. So because of this reason, we have decided to develop a new downscaling algorithm that focusing not only on downscaling emissions, but also on downscaling, in particularly the energy variables and the energy related carbon emissions. So in order to give you an idea of how the algorithm works, we are using data that in the first place are coming from internet assessment models. And then we are also combining the regional information from internet assessment models with the GDP and population projections that we have available at the country level that are coming from the SSP database. And basically by combining this information, we develop what we call some long-term integrated assessment model projections that we use as a reference for the long-term, for our long-term trends. And then we also use historical data at the country level, in particular data that are coming from the IEA, the International Energy Agency. And we assume that at the beginning, countries will try to follow as much as possible the historical trend. And then at a later point in time, they will gradually converge to the regional long-term benchmarks that are derived from regional internet assessment models. So therefore, the timing of convergence, it is a key parameter in our downscaling algorithm. And by playing around with this conditional convergence parameter, we can get a range of pathways at the country level. Then another nice feature of the downscaling algorithm is that we can also introduce domestic policies, and we take into account INDC in 2030 and also the mid-century targets in 2050. And after we do the policy adjustments, we get the final national pathways at the country level. So in terms of the steps, we start by downscaling first the final energy variables. And essentially here you can see a table with all the variables that we are looking at. Then after that, we downscale the secondary energy variables. Then we go into the primary energy, and finally, we downscale the energy-related carbon emissions and also CCS sequestration from biomass and from fossils. So to start with, I would like to show you how we downscale the total final energy demand. In this graph, you can see the energy intensity for all the Western European countries from 1970 to 2015. So essentially here you can see all the historical data for the energy intensity against GDP per capita. And basically each color is a different country in the Western European region of the message model. Then in order to have some additional reference point on this graph, we can also add other countries like China, India, Japan, and the US, just to get some reference point on this graph. And the clear message that you can see from this graph is that with increasing GDP per capita, we should expect a declining energy intensity. Now, this is also confirmed by the Internet Assessment Model results. And in this, this red line here, it is essentially a baseline scenario from the message model from 2010 to 2100 for the Western European region. And as I mentioned before, we initially assumed that countries will try to follow as much as possible the historical trends. And then at a later point in time, they will converge to the long-term projections, which is this red line that you can see in this graph. And this is essentially by playing around with our convergence parameter, we can determine a range of pathways at the country level that are all these multiple lines that you can see here in this graph. Now, we also need to determine somehow some default or some standard parameterization for our convergence. And for our standard parameter, we actually choose the timing of convergence depending on the quality of the historical data. So if we get a very high R-square for a particular country, then we assume a slower convergence to the long-term projections. But then if the quality of historical data is not very good, then we assume a faster convergence to the regional Internet Assessment Model results. Then I would like to show you how we downscale the secondary energy electricity, the electricity mix. And for doing that, we are not just looking into the historical data, but we are also looking into additional criteria. For example, we use the governance indicator developed by Marina Andrijevic and co-authors. We also use supply cost curves for the downscaling of solar and wind technologies. And we also look into the planned capacities because we know that there are some countries that are already planning to invest, for example, in gas power plants. And we also know what is the age structure of the currently operational power plants. And this information is very useful to enhance our downscaling, in particular for fossil fuel technologies. Even in this case, we can play around a little bit with those different criteria. And essentially, if we use somehow some standard criteria weights, so our default assumption, you can see how the results look like for Great Britain, for example. This is a downscaling of the electricity mix from 2010 to 2050 under a message current policy scenario, and also a comparison with historical data from 1990 to 2010. For example, in this case, you can see that gas will increase over time and nuclear will be phased out by 2050. But as I mentioned before, we can also assume different criteria weights. So what we can do is to play a little bit with those weights and essentially run the downscaling algorithm with some random weights. And if we do that, we get the graph that you can see on the right-hand side. This is just focusing on 2050, and you can see how the distribution of the results changes if we essentially play around with the electricity criteria. And this is essentially a sensitivity analysis of how the results might change if we use different criteria for our downscaling. And in this particular case, gas shows the biggest uncertainty for the UK. Now, after downscaling the electricity, the secondary energy variables, we can also look into the primary energy and emissions. In this case, you can see the results for the United Kingdom on the left-hand side, and then Germany on the right-hand side. We simply assume some conversion losses from secondary energy to primary energy. And here you can see also what are the energy-related carbon emissions under a current policy scenario. We can run the same analysis also for a 1.5 pathway, which is the graph that you can see here. And essentially fossil fuels will be gradually replaced by increasing renewable energy. And here you can see that the energy-related carbon emissions will gradually decline over time and approach zero by 2050. Now, a nice feature of this 1.5 pathway is that we also take into account domestic policies. In particular, we take into account the INDC target in 2030, and we also take into account the mid-century strategy of 2050. So essentially, when we run this scenario, we also try to make sure that each individual country is also able to reach their own domestic target, and this makes our results a little bit more realistic, and therefore can be used also for to advise policymakers. Finally, I also would like to show you that the results of this downscaling algorithm can be also used for different regions, not just the Western European region, but also, for example, the Sub-Saharan Africa region. In this case, I'm just showing the results for emissions of CO2 from energy.
2 minutes.
Okay, thank you. And in this case, essentially, the main countries that are taking the biggest chunk of the emission are Nigeria and South Africa. Also, another example here on the right-hand side is the downscaling for the centrally planned Asia region, which is pretty much dominated by China in this particular case. And then we have also, again, the results for the Western European region with a breakdown by countries. In this scenario, Turkey will become the biggest emitter by mid-century. And finally, also the results for the Pacific OECD region that basically comprise Australia, Japan, and New Zealand. So now just to jump into the conclusions. So we are presenting a new downscaling algorithm that focuses on energy variables, in particular the final, the secondary, and primary energy results, and also the energy-related carbon emissions. So the main goal of this tool is to essentially assess the feasibility space of the Paris Agreement by also playing around with the different parameters that I showed you before. We can change the convergence assumption, we can change the criteria that we use for the downscaling, and if we do that, we can really assess what is the feasibility space of low carbon emission pathways at the country level. Another feature of the downscaling algorithm is that we can also take into account policies, so not just the 2030 INDC target, but also the 2050 long-term century strategy, mid-century strategies. And finally, we can use this tool to provide guidance to policymakers on how to enhance the current level of ambition of INDCs and also the long-term targets, and essentially see how basically we can align the current policies and current INDCs with the long-term goal of the Paris Agreement. So that's it from my side. Thank you.
Thanks a lot, Fabio. Very interesting talk. Are there any questions from the audience? I have one to ask in the meantime. I mean, very interesting to see also the different knobs and pretty granular information that you're taking into account for the downscaling, particular policies and so on. In terms of the high-level tweaking, my understanding is that the convergence parameter is a key one. One thing that I was wondering about, it seemed to kind of show on the figure that you presented that for countries that are comparatively low already within a region, if you go with fast convergence, you can create short-term artifacts in the sense that the country can actually go up because it's kind of lower than the region, right? Go up and then come down again, which would sound a bit odd that the best performers kind of deteriorate and then kind of only later on catch up again with the rest. So I was wondering, is there anything? Have you looked at this? Is this something you can? You've thought about dealing with one way or the other?
Yeah, thanks, Volker. That's actually a very good question. So yeah, I think usually one of something that we have experienced in the past, especially also for the Western European region where we have very good quality of data, is that some countries, for example, show an increase in energy intensity. And in this particular case, what for example, what we can see is that it doesn't really make a lot of sense to increase, to assume that the energy intensity will continue to increase in the longer term. So for example, if we see that the slope of the historical trends is completely going in an opposite direction compared to the longer term, we assume a faster convergence. But as you mentioned before, yes, it is possible that a country that is below the average maybe will at the beginning increase the energy intensity and then go down again to the following the regional trend. That is something that it is possible, but in a sense that could probably happen if there's also an increasing trend in the historical trends. So so in a sense there will be still a continuation of the historical trends and then gradually a convergence to the long-term trend. But that's probably something that we have to also look into that a little bit more in details to see if there are also, some countries where there's this problem. But usually at least we have run that for the NGFS project, and usually the results look okay for most of the countries.
Yeah, thanks a lot. I actually have an idea how one could try addressing that, but let's not roll this out here. We have another question from Nico on your presentation. Nico, please.
Yeah, thank you very much. Thanks, Fabio. Nice to see the tool is really working now with many regions also. I have a question on the general understanding. Imagine you have one region that is made up of two countries. And one is more gas and the other is more coal dependent. And now you have the scenario for the region. And if now you impose you apply the downscaling, would that mean that the percentage emission reduction would be equal in the gas and then the coal dependent regions, or how would that be allocated? That would be interesting to know. Thank you very much.
Yeah, thank you, Nico. That's a very good question. So it wouldn't be an equal allocation, but it would be so essentially because also we are looking into the different sectors. So for example, we have the emission coming from the electricity sector. And for that, we look into the individual power plants of each country, if they are gas related or coal related. Then we also have solids, we have also liquids. So essentially, we are looking into all the different sectors. And for example, for electricity, we are looking into different criteria. So we use some supply cost curves for downscaling renewables. We are looking into the age structure of currently installed power plants for downscaling electricity from coal and from gas. So essentially, the allocation depends on how we play with the criteria that we want to look at. If we want to give it more relevance to the age structure and the planned capacities of installed power plants, or if you give it more relevance to the supply cost curves, or if you want to make more prominent the historical data or governance indicators. So depending on how we play around with those parameters, the allocation will change also of the emissions, because it will change the electricity mix and the primary energy mix of the different countries. So it will not be an equal allocation, but it really depends on how we play around with the parameters.
So last presentation in this session is by John SAMPEDRO. presenting an R tool that estimates air pollution health impacts and impacts on agriculture. John, the floor is yours.
Yes, so today I want to present this tool called rfasst, which is an R tool to estimate the air pollution impacts on health and agriculture. And it's a tool that we have developed here at KREY by a disciplinary research team, and also in collaboration with some colleagues at GRC. So the motivation for developing this tool is like we know that air pollution is a major health problem, right? And now it causes around 7 million deaths globally, very concentrated in South and East Asia, but also in many parts of the world. And most of these deaths has been attributable to exposure to fine particulate matter, to PM2.5, but there are also other pollutants that are creating like these premature deaths, like tropospheric ozone or NO2, right? So we know that it's true that air pollution has considerable decrease in the last years, and therefore the air pollution related impacts. And I created an animation that you can see there based on data from the Institute of Health Metrics and Evaluation. And we know that air pollution has decreased, mostly because there has been an increase on access to modern energy carriers, like for example, improving the access to use clean fuels for cooking. And also many countries have implemented like emission controls in recent years. For example, the SO2 emissions has decreased in China because of the implementation of these end-of-pipe SO2 technologies, right? So, but still, even though they have decreased in the last years, we know that the countries are still very far from the air quality thresholds that have been established by the WHO, which has actually been updated now in September 2021, becoming even more stringent. And because of this, now it's estimated that more than 90% of global population breathes unhealthy air, and that's why we still have this big amount of premature deaths attributable to air pollution, right? Also, as an illustrative, just to show the importance of this problem, I wanted to use this figure from a paper that we published early this year, led by my colleague Tom van Dijk, that we compare the deaths attributable to air pollution, the x-axis, in 2019 with the deaths attributable to COVID-19 in 2020, right? So just there is a lot of information of this figure, but just wanted to show that there are still many countries that are more affected by air pollution, and there are many things to need to be updated. But I think that is a good illustrative example to show which is the importance of air pollution in terms of human health, right? So, and on the other hand, apart from being an important factor for human health, we know that air pollution, through the concentration of tropospheric ozone, has also a direct negative impact for crop yields, right? And then you can see a figure that on a paper that we published last year, that we estimated the relative yield loss attributable to ozone exposure for different regions and periods and for different crops, right? So we estimated that you can see on the figure that these relative yield losses could account for 10 to 20% of different countries and periods. So we thought that these numbers are especially important for addressing some of the most pressing problems, right, currently. So for example, this is going to have an impact for address food security problems, because we can see that ozone is going to be harmful for some staple commodities like wheat that are basic for human nutrition. Also, in terms of economic losses, these relative yield losses are going to have an impact on agricultural sector and overall in economy-wide. They're going to have an economy-wide impact. And also, like for the energy sectors, we know that some of the oil crops, like soybeans, for example, are especially affected by ozone, right? So also depending on which is the penetration of biomass technologies in the future, we think that ozone is going to be important. So overall, we think that ozone is also going to play a role on future scenario analysis, right? So in this context, we know that this health and agricultural impact has been of high interest for the integrated assessment modeling community here. And just screening some literature for recent years, you can see there an illustrative table to show how many different models, but not only single models, also there has been like multi-model comparisons to explore the health impacts attributable to air pollution for different scenarios, but also that there are some papers using these integrated assessment models that has analyzed the agricultural impacts for the different scenarios, right? However, we know that these integrated assessment models, or models like report air pollutant emissions, right? But they do not incorporate atmospheric or meteorological information to translate from the air pollutant emissions to concentration levels, and therefore to estimate directly the health and agricultural impact, right? So normally in these papers and in most of the papers, like these integrated assessment models or the model outputs need to be connected to additional air quality models or emulators. So one of the most used air quality models in these studies here is TM5FAST, that I think that some of you will be familiar with. But yeah, just a brief description of this model. TM5FAST is a surreceptor model which is developed by GRC, by Rita van Dingenen and the team, and is designed to estimate ambient air pollution and the subsequent health and agricultural impact, right? So basically the model, like, it's a linear simulation of the emission concentration relationship, which has been pre-computed by a full chemical transport model, right? So in the right from the TM5FAST model documentation, you can see a scheme on how this model works. So the model reads in different pollutant emissions that can be produced by integrated assessment model or by emission inventories, and then estimates the PM2.5 and ozone concentration levels and the subsequent impacts, right? So the rationale behind these emulators is like try to find a balance between the running time and the accuracy, right? So in terms of time, running such an emulator can take minutes versus days or even months, depending on the analysis that you want to do if you use a full chemical transport model. And similarly, it's important to try to validate the values that you produce versus the full chemical transport models. And here is one example on the TM5FAST documentation paper by Rita van Dingenen, that they compare like premature deaths attributable to PM2.5 exposure using TM5FAST and the full PM5 chemical transport model for two scenarios, which I think they are frozen legislation and mitigation scenarios run by IIASA some time ago. And you can see there on the validation figure that the numbers are quite match. So the numbers supported with the emulator can be like can be used or can be consistent, right? So we know that it's an open access version of TM5FAST, which is a web-based version of the model. However, this is designed for making a static comparison, so it has some problems to compare, to make these multi-scenario, multi-year comparisons, right? And the version also is not flexible to change the inputs and outputs. So basically, in summary, like this open access version is not directly connectable with integrated assessment model or integrated assessment model outputs, right? So yeah, in this context, we thought it would be good to design this rfasst tool to make the TM5FAST model available as an accessible R package that could be readily used for estimating air pollution and the subsequent impacts for alternative what-if type scenarios that are normally modeled with integrated assessment models and with GCAM in our case, right? So basically, rfasst is a flexible package which consists of a number of different functions to estimate different things, but are classified or are divided in 4 different modules, right? So in the first step, we take the emissions from, in this case, GCAM, and we rescale them to the regional disaggregation of TM5FAST, doing some other pollutant-related adjustment. And I think this is very related with the talk that we have just heard. And also we have like different modules like to estimate like concentration levels at PM2.5, ozone, the additional health impacts in terms of mortality, years of life lost or dailies and the associated damages, and the agricultural impacts, right? So the tool includes additional input information like baseline mortality rates or BSL default values that can be edited by the user. And in terms of outputs, the tool will generate different CSV files or tables, maps, and animations generated with the RMAP underlying software. So in these 2 minutes, I will show some examples for a GCAM baseline scenario with no climate policy. So here you have an animation for estimating PM2.5 concentrations for different regions and periods. This is the output of the second module. Then we can also see an example for premature mortalities attributable to PM2.5 exposure for different regions, also different causes and periods. But again, we can calculate years of life lost, dailies attributable to PM2.5, ozone, and also all of the associated economic damages. And finally, here an example for the agricultural production losses by region, crop, and period, right? So this is a bit more complex because, again, we need to connect with the GCAM model to project agricultural production and prices, but this is an example of the output. So just to finish with some final remarks, this package is available in GitHub, so you have the link, and if you're interested, any contribution is welcome. Also, in the repo, you can find a complete documentation website, and we are preparing a a documentation paper that is currently under review at JOS, and you can see the team contributing here, including Sara, Chris Vernon, Steve Smith, Stephanie Waldorf, and Rita van Dingenen. And just the last point I wanted to make is like, it's modular, and because it's important to think about, like, we design this in a modular way because we want this to be expandable to other models, right? So, and as an example, if you are using another integrated assessment model and you just modify the first model to rescale the emissions from your model to the TM5 disaggregation, you will be able to easily estimate concentrations and health impacts. Agricultural are going to be a bit more complex, but having this modularity is going to allow the tool to be extendable to other models. And just like some plant developments that are going to depend on future project development, so I would like to update the functions to the latest global burden of disease study. I would like to downscale to finer scale, but it will require some time and some project dedicated to this. And also would like to improve the morbidity calculations, right? And now are based on fixed radius. Yeah, there you have my contact. If you are interested on the tool, please do not hesitate to contact me. And that's what I have.
Thanks a lot, John. That was great. Before anybody writes to you an email, they have the possibility here to ask direct questions. I had something while people are gathering their thoughts. I had one question. I seem to recall that there was an R version of FAST also developed by colleagues at CMCC. I don't remember whether this was open source or not. I was just wondering whether there's any relationship of your work with that work, or whether you've been aware of it.
Yeah, I think that there is a fast version for the which model, I think, but I don't know if it's like this, like accessible. I don't know I have not coordinated with them for this work. Perhaps we can, if they are interested, if anyone is in the call, perhaps we can coordinate on that. Yes, and yeah, for sure.
Yeah, I mean, I just looked it up and posted the links in the chat. It was just interesting because from a community perspective, which INC is all about, it would of course make sense to kind of join sources, in particular for kind of future development and maintenance. Then,
yeah, absolutely. Yeah. I will check it and contact the team for sure.
Okay, we have Martin is adding to this, saying that there's also a fast implementation in Python that is used within the image model, so could really be a community activity to maintain that. I mean, but this is great, right? This is what this meeting is all about in terms of generating community activity and exchanging information and yeah, basically better use our resources jointly.
Yeah, absolutely. I will check the other tools there, and please contact me, and we can do things like for future developments together, and I will be happy to do so. Everything like this is designed to be open access and community oriented. That's why we designed the different modules. So
great.
That's the idea behind this.
I had actually one remaining question to Sara on the harmonization, if I may drop it in now. Sara, the techno-economic harmonization is something, I mean, we've done a study a few years ago on specifically focusing on power sector, where usually information is best and also coherence in terms of representation across models. And one of the outcomes of this comparative study was it's actually not so straightforward to harmonize. Problem being that representations of even something like the power sector is very different, right? There are models that have 5 different coal power plants without CCS. And then there's other models, and those can be often then static in terms of, I mean, representing a subcritical, a supercritical, an ultra supercritical steam coal power plant. And then you have another model that has just one coal power plant, basically being representative for the coal to electricity route, and implicitly in its parameterization, assuming kind of a transition of the dominant technology within this one, right? So assuming that the share of supercritical and ultra supercritical coal power plants will grow over time, and therefore efficiency, but also cost of that technology increase over time. This makes it, in my understanding, non-trivial to actually even do a simple harmonization, because you're really not comparing apples and apples in many cases. And of course, it's a very large number of parameters that you potentially have to harmonize. So I was just wondering how you practically dealt with this challenge.
Yeah, that's an excellent question. I mean, and we found it challenging during the project that we carried out as well. So the way that we wanted the procedure based was on absolute, let's say, transparency of the model input, so that we develop first a database. We gathered together this input for the techno-economic, techno-economic characterization of key technologies per sector. And so we did this for power power and transport, and yeah, so the approach was based first, let's say, primarily on this, let's say, sharing first of what was the common knowledge of the technologies that each model had, and there was a big effort of technology mapping when that was possible across the models that had these options available, and that was more true for the bottom-up models as opposed to the top-down models. So we started, let's say, in the first instance with this, sharing of this input data, and we had the brainstorming on certain input because each model had different assumptions. So at the end, it's not, let's say, it's not an effort which is finished in a way. We only started, let's say, triggering or identifying the aspects that were more, let's say, relevant to actually guide the solution, and that was first in terms of costs and efficiencies. But then we left other aspects, out, such as growth constraints. So it is, I think it is an ongoing effort, and I think the main message that we obtained at the end of the project, at the end of that part of the project, was really the importance of having databases shared with the community, with the input assumptions that are shared, and so transparency of the input data, and an ongoing effort of brainstorming and discussion with the modelers about how the input data are used. So yeah, it is still, yes, in the end, probably, I guess, and then I would conclude with that, is that it is important to see what is the model response to certain variation of the input, so that is also, even if it is not a full harmonization, because that, I think it's not really feasible to actually fully harmonize the model in those techno-economic input, but at least you have some guidance about how these changes would actually affect the results. And I hope I answer the question. I mean, it's an ongoing, I think, effort there. It's a challenge, actually.